Hello, welcome to video number 8 in the wave nature of light. Very quick one on dispersion. Now dispersion is a term that's used when we see a visible separation of the colours of light into a spectrum. And we've probably seen that already when we've looked at a rainbow, for example. But let's just go through what it means and how it happens. It really is a variation of refraction. And so it's a very narrow use of a very specific situation of refraction, whereas refraction can occur in a variety of environments and interfaces. Dispersion is pretty much limited to this definition here. So we've seen it when we've shone light into a prism. Here the light comes in, recognizing that this light is made up of all the wavelengths of light, all traveling at the same velocity for air. Now it's going from air into, say, glass, and so that's going from less dense to more dense, so the light will refract towards the normal, and to varying degrees depending on the wavelength, and so the red light is refracted less than the violet light. Then travels through the prism, comes to this interface, and we have a new interface, and now it's going from more dense to less dense, and so it will refract away from the normal. And again, each of these would be considered there. I wonder if I can draw on this. Yes, I can. Each of these would be considered, helps if you have a colour that you can actually see, would be considered their own interface for each of these lights, and so that would be the normal for the violet, whereas this is the normal for the red light, and this is the normal for blue or whatever. Okay. And if we go back to that, and so that's why we can see this rainbow here. Okay, and there's a picture of it. Notice that there's some light that bounces off this interface here, so that means that this interface isn't 100% transparent, and so it acts as a partial mirror. That's what that is. And this beam here is because this interface also acts as a partial mirror, and so some light is bounced off, and there'd actually be some light going in there, maybe coming in there if we were really keen to look at it in much more detail. And we've all seen a rainbow, and hopefully we might understand why, or the conditions that you need to see a rainbow. First of all, it's got to be sunny, but there's also got to be water droplets in the air, and you've got to have the combination of the two. And the sun's always got to be behind you to see a rainbow, and there's an old saying, of course, that if you can get to the bottom of the rainbow, you'll catch a leprechaun, perhaps, with a pot of gold. And of course you can't reach the end of the rainbow because this rainbow is specific to this person. And therefore, if this person moved, the rainbow would move correspondingly. And if someone was standing next to the person looking at this rainbow, they would see a slightly different rainbow. Now you can also get double and triple rainbows, and you can get what's called sundogs in really cold climates, where it's the ice crystals causing the rainbows, which are also interesting as well. Ask me and I'll show you a picture of some. How does it work? Well, there's the sunlight, there's a person observing it, water droplets are all over here in a mist, sun goes in, this interface the light gets refracted at this interface, so split into the spectrum. This interface now acts like what's called total internal reflection, which we're just about to do in the next, in the second next video, I think. But basically, it acts like a mirror, so the coloured light, all the wavelengths bounce off that, come to this interface here, and you actually get transmission of the light, and again you get refraction, and therefore you see the rainbow. And so this droplet here is actually providing the red light to the eye, whereas this droplet here is providing the violet light to the eye. And that's how the different droplets all go to make up the rainbow. Yeah, there you go. In the next video we'll look at apparent depth. See ya.